Okay, can you see the can you see the PowerPoint presentation? Hello. Okay. Okay. Can you see the board? Can you see the board? Okay, no problem. Okay, then I'm starting. Now, in this reanalysis 4, this is reanalysis 4. You will be getting it. Okay. So today I'll cover what is interval, what is neighborhood of a point, what is the interior of a point and set, and what is called an open set. Okay. So someone has entered, I think. Yes, my boss. Okay. So today I shall start this one first with this interval. Now see, you know what is written here. You know it already, but you don't know exactly how it is, how it can be described. Okay, this is interval. Interval we are using it. Say, let A and B belongs to the set R. So set A is equal to say 2 and B is equal to 3. So 2, 3 belongs to the real number set, the real number. Now, suppose A is less than equal to B. We know that real number set uh, is a it follows the order property. Okay, so we can easily set this one, A less than equal to B order property. The set of real numbers. So we now construct a set of real numbers from the real number set, just like S. We are using this notation. So x comprising that x must be a member of R and it must be between A and B, but it should not be equal to A and B, or simply A B. It can be written as simply first bracket A and B. Okay, so in this way you can read it. Okay, then uh, this called the it is called the interval on the real line. When you write the set as this one, we write this interval as like this, and we call it as closed interval. The set S is written as it is semi-open interval. Why? Because this side is open and this side is closed. Closed means the points just right of B is not allowed, but points of left of A is allowed. Okay, and this is called, so this is called left open and this is called right open. This set, this is called, oh sorry, I made a mistake here. Let me check it, correct it. So this should be like this, and this is okay. This should be like, A comma B. Okay, left or right. This subset of R is called the infinitist set. That is, all numbers greater than A is called the infinite open interval and represented as A to infinity. Similarly, this can be, that is, uh, minus infinity to B. So all number are less than B, but it is up to minus infinity or semi-closed in interval. it can be also be semi-closed. Okay, so the real line is denoted as this one. So this is the way we are representing interval in our real number set only. Okay, now uh, second definition is that what is called the neighborhood of a point. Neighborhood has been represented as NBD. Okay, in short, it can be represented as NBD. Now, a set, this set is said to be a neighborhood. This is a neighborhood set. Remember this neighborhood set of a point X. So, if there exists a epsilon and epsilon, this is an epsilon greater than 0. So epsilon is a real number. Uh, it may be very small quantity, it may be any real number, but it must be positive. Such that, so interval we have represented x minus epsilon and x plus epsilon will be a, so this is an interval. So this interval must lie wholly, completely within Rx, within this neighborhood of x. As for example, total R. Now this Rx can be the real number. This neighborhood x. This is the neighborhood x. Actually, this is n written uh, in a script. Okay, script language as, so neighborhood. This neighborhood can be the whole real line. Okay, so the whole real line can be the neighborhood of any real number, and here R is open. Now, if this can be represented, our case, okay, if this can be represented, um, uh, any set uh, containing x with such an interval, then it is called an open interval, open set. The set Q is not the neighborhood of any of the rational number. Hence, Q is not open, because between any two, because just Q is a rational number, but there may have some points, irrational numbers are there. So you cannot get such an interval around every rational number. Okay, so in that way, Q is not an open set. You cannot get. Now, a finite set is not the neighborhood of any set. Remember this fact. Okay, only because that an infinite set cannot be a subset of a finite set. So a finite set. Okay, so this is an infinite set. Epsilon, there are infinite points between x minus epsilon and x plus epsilon. So an infinite set cannot be a subset of a finite set. That's why that is the reason. Now we have to prove two theorems that if either m or n are neighborhood of a point x, then their union and their intersection are also neighborhood of n. Okay, this we have to follow, prove. Okay, next slide. Now let M is a set, neighborhood is a set, and that is contained in R, and N is also a neighborhood of that point X. So let X belongs to their union. This implies that X belongs to M or X belongs to N. So there exists epsilon that is greater than 0 from the definition of the neighborhood. That's x minus epsilon and x plus epsilon belongs to M. Or this interval is contained in N. So these two are true. Okay. So if these two are true, then this interval also belongs to this union. So is also a neighborhood. Now second one is that same condition, but here it is intersection. So this means and both. So x belongs to M as well as x belongs to N also. Oh, here it is, I made a mistake. It must be R. It must be N. Okay. So I will check it and I will send it to you after correction. This is N. Okay. So so x belongs to N. Now we make another interval in for M and another interval for N also. So here it is epsilon 1. So this interval is x minus epsilon 1 and x plus epsilon 1, and that is contained fully in N. Contained fully, remember this term, and x minus epsilon 2 and x plus epsilon 2 contained fully in N. So here x1 and epsilon 1 and epsilon 2 is greater than 0. So let epsilon is the minimum of these two. This implies x minus epsilon and x plus epsilon both is contained in M and also contained in N. So this epsilon interval has been contained in the interval. So this is also another interval. So intersection and union are also neighborhood of x. This is an important theorem for neighborhood. Next, I will come to the interior point. A point x is contained. Interior point is a very important conclusion uh, for defining open set. One open set is that every interval, if there is any interval which is fully contained in the parent set, then that small subset is an open set of the parent set. Now here is we are it is going to be clear more. Suppose x is belongs to the S and S is a subset of R. Okay. Now this x is called an interior point if a neighborhood of x, say epsilon neighborhood, is fully contained in S. Okay. So you choose a neighborhood, however small, that must lie within the set S. Then this set, then this point X, if it lies fully within S, then it is called the neighborhood of S. Now, if epsilon runs over infinite values, so this set contains infinite number of points as well as there are numerous numbers of neighborhoods of a point of a set of a point x. The set of all interior points, now there should not be one point. The set of all interior points of S is called the interior of the set S. Now this set is denoted as S to the power 0. Okay. A set is called open. Now a set is called open. This is the definition of the open set. A set is called open if either S is equal to 5, that means either S is a an empty set, or every point of S is an interior point of S. That means there is no other point within the set which is not an interior point of S. So S0 is equal to S. Okay. In other words, S is neither null set or neighborhood of each of its point. Okay. So this is the definition of an open set. An open set, so R is a set, S is a subset. Whether the subset is open or not will be decided by the fact that if every point of S is an interior point of the same set. Okay. Now this following points seems to be obvious. The interval AB is neighborhood of all its points. Interval AB. All its points lies between A and B. Hence open. So this interval is open. Okay. R is the neighborhood of all its points and hence R is open. Okay. Q is not the neighborhood of all rationals, hence Q is not open. A finite set is never the neighborhood of its points, as I told earlier, hence it is not open. Interior of a finite set, so interior of a finite set is null. Now this fifth condition, you think over it, say suppose a set comprising only 2 points, that is 1 and 2. 1 and 2. Okay. So open set, there must be some open set 1, but a singleton set is never open. Singleton set 1 comprising 1, no other points. Okay. And comprising 2, no other points. So these two sets, finite sets, are interior set is null. That means phi. Now if you remember all these definitions, you can, these are all theorems. Okay. So that every open interval is an open set. So what is open interval? We know this is our definition of interval, open interval. Okay. So this is our definition. You can recall it, this definition only. This is not open, this is not open, this is not open. Okay. So you can recall it. Let I is the interval, this one, an open interval in R, and let x is equal belongs to I. So x lies between this. Okay. Now we are declaring it here open, but we have to prove it that this is open. But then interval. Now we have to prove that this open interval is an open set. Okay. We can choose numbers C and D. Now see, open interval and open set, is there any difference? Yes, there is a difference. Now that difference will be clear here. We can choose number C and D between such that A, there is, that is between A and C, A and X is a number. So between A and X, C is a number. And this follows from the density property of the real number set. And there are numbers where between X and P there are numbers D. Okay, there is some mistake here, I will correct it. So I is this set open interval, it contains C and D. So AB is the bigger interval and CD is the smaller interval, and X belongs to CD. This shows that AB is a neighborhood of X, spelling mistake, of X. So since X is arbitrary, so every point of I is an interior point of I, and hence I is open. So this set is open. Okay, because this is also open. So and this interval X belongs to X is an interior point, because that set wholly lies between AB. So from the consideration of interior point, this X is an interior point of I, so I is open. Now interior point of I, interior point, a set is open if every point, since X is interior point, so interior point, any X is the interior point, but for each X you will get different CD, and these are neighborhoods. So each point x has neighborhoods wholly lying between within the set AB. So AB is an open set. So starting from the open interval, we are getting AB as an open set. Now the reverse can also be proved, so that every open set is a union. Now second one, very important conclusion. So that every open set, okay, this open set is union of open intervals. Now see, let S be an open set and X belongs to S, which is a subset of R. Then X is a neighborhood of X according to the definition of the neighborhood. So there exists open interval. From this, there is the open interval Ix. So Ix is contained in S. Now S can be considered as infinite union of sets of X. So this X has, then Y for Y, this IY is there, and then Z is there. So S is nothing but union of all these X, Y, Z's. Okay. So we have written union over X over of all X, and that is contained in, because Ix is contained in Ix, so union over Ix, and this union cannot be more than this Ix due to this. So these unions are nothing but like CD. Okay, so S is nothing but union over Ix. So and Ix's are the open intervals. So union of open intervals. So any open set can be represented as union of open intervals. So this is your second conclusion, A, B. Next, the interior of a set is an interior of a set. Now S0 is the interior. So I have written it here, Si. So it must be S0. S0. There is also S0. 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 Okay. So this is C is interior of a set is open. Okay. Now interior of a set. Let S0 be the interior of the set. Okay. First, S0 be the interior of the set S. Now if S0 is equal to 5, then it is open, because obvious reasons is always open set. Now if S0 is not equal to 5, okay, this is also S0 is not equal to 5. Okay, then what happens? Then uh, S0 is not equal to 5. Then X is an interior point of S. Okay, so there exists an open interval as per the open Ix, such that this holds, as you know. Since an open interval is a neighborhood of each of its points, open interval is a neighborhood of each of its points, then Ix is neighborhood of X, but this asserts, that means this proves that every point of Ix is an interior point of Ix. So Ix contained in S implies Ix is contained in this set. Okay, that is Ix is contained in this set. And this means that X is an interior point of S0. Since x is, since x is arbitrary, so every point this can happen. So S0 is an open set. This is the condition of the open set. So interior of a set is an open set. Now the next one, D, very important condition, that the union of arbitrary family of open set is open. Now this is very important, as because that this is in the sixth semester, this will be uh, treated as a very important property of a topological space. Okay. Now, union of arbitrary family of open sets. Now there are open sets and their union is open. So let G be the arbitrary family of open set and let Gi belongs to G for all I belongs to A. Now Gi, that is G is the arbitrary family of open set. So Gi is are the their member arbitrary family for I belongs to M, and G is equal to union of Gi. Now let X belongs to G. Then X belongs to Gi for some I. Okay. So this implies that any of the Gi is contained in G. So G is the larger set and Gi is the smaller set. So but this implies that Xi is an interior point of Gi. That is, there exists an open interval Ix such that X contained in X belongs to Ix, that is contained in Gi, and Gi is contained in G. And this again implies that G is the neighborhood of Gi, since neighborhood of each points, thus implying that every point of G, X is a point of G, is an interior point of the G. So G is open. So but what is G? G is nothing but the union of all Gi. So union of arbitrary family of open sets. So Gi are open. That's why their union is also, there is G, there is also open. So this is about D. The intersection of a finite, here it is not arbitrary, finite, of open set is open. That is very important. We shall prove this theorem for two sets only. Okay. Let X belongs to G1 and G2, and G1 and G2 are open sets. Okay. So X belongs to G1 as well as X belongs to G2 at the same time. So if G1 and intersection G2 is phi, then we have nothing to prove. But suppose it is not phi, then this implies that X belongs to G1 and X belongs to G2. This implies G1 and G2 are both neighborhood of X. So their intersection is also a neighborhood of X, as we have proved earlier. And since X is arbitrary, so G1 intersection G2 is an open set by the definition. Now we have extended the reasoning. Now let us take another step 3, and by using the same this treating as a single set. Okay, so G1, G2 and G3, so we can prove that this is also an open set. In this way, continuing this process, we conclude that if we continue with finite number of sets, finite times, then this up to n is an open set. Okay, so but you cannot continue it infinitely. Okay, intersection of a arbitrary number of open set may not be an open set. Now see Qn. Say n is the 1 by n. So a is a rational number and u minus 1 by n and a plus 1 by n. Similarly, this is an open set and n belongs to n. But intersection of this is nothing but a singleton set. You continue intersection of this. So first is a minus 1 and a plus 1. Then a minus half and a plus half. Okay. Then a minus 1/3 and a plus 1/3. Go on intersection, taking intersection. So say this cells are this simple intervals are getting shorter. So what will happen in the at the end? their intersection will be like this. And so a singleton set is a closed set, so it is not an open set. So this may not be an open set. Okay. The interior of a set is the largest open set contained in S. This is very important. Okay. The interior of a set is the largest open set contained in S. So suppose we are having a set S and we are having a set interior to it. Now, which one is the largest open set that is wholly contained within the set S? That is nothing but the interior of the set. Now, you will see that interior of the set, just imagine a circle. Just imagine a circle. Okay, let me show you here. Uh, Imagine a circle. Okay, imagine a circle. Suppose this is the our set. Now, except omit the points of the in the boundary. Omit the points in the boundary. Okay. Take the points of S. S0 is the interior of the interior of S if you omit the points in the boundary. So there are boundary many points. Okay, these are the boundary points. Okay, you omit this point, so you will get a set. Let that set is known as the S0. Okay, that is the interior of the set. Just omit the boundary of the boundary points of this set S. Okay, this is the meaning what I want to tell you here. It is the largest open set contain. So any one of the boundary point, if it enters, so that is not the interior of the set. Okay. So let G is contained in G belongs to S and G is open. So G is a set, it belongs to S and G is open. Then X belongs to G implies that X is an interior point of G. Okay. So if it is the interior point, so G is a neighborhood of X. That is, X belongs to G contained in S. This implies that S is a neighborhood of X. So if S is a neighborhood of X, so X belongs to the interior point of S. And so for every X belongs to G, X for every X, so you can change from X1 to X2 to X3 and X3, so on. That means for every point X, that X belongs to this interior point. So G is contained in S0 for every open set G. Again, S0 is contained in S. S0 cannot be more than S because S contains the boundary points. So S0 is the largest open set in G that is contained in S. So this implies that S0 is the largest open set. Now, this is a very important conclusion that S0 and S at S0, whether they will be equal or not, you cannot say they are equal. Okay, so at what point they will be equal will be starting point of the next class. Okay, now today I am not going to give you the details, the assignment. All of you have sent the assignment, I think. All of you, mostly all of you have sent the assignment. Mostly all assignments are correct. I have checked it. Not all, but I have checked most of them. So these are good. Next class, in the next class on Wednesday, I will give you assignments. Before that, on this is your, now you can check your syllabus also. You can check your syllabus also. I am just showing you the syllabus. Just think over it. This is your syllabus. Can you see? Can you see the syllabus? All of you? Hello? Can you see my board? Now see. Okay. See how much we have concluded. Review of the algebraic and order properties has been done. Epsilon neighborhood of a point I have discussed. Idea of countable, uncountable sets and uncountability in are discussed. Bounded above sets, bounded below sets, bounded sets, unbounded set, supremum and infinite. This also discussed. Then completeness property in R and its equivalent properties. That is well ordering principle and all these things has been discussed. Archimedean property, density of the rational and irrational numbers in R, that there is also. Now I am here, open set, close open set with intervals and intervals. Okay, open set, intervals, and neighborhood is coming. But neighborhood, actually neighborhood, epsilon neighborhood there in your point, that has been covered here. Okay, so closed set, derived set, limit points of a set will be the discussion point of our next class. Then Bolzano-Vistas theorem, which is our target, and these are all preparatory for Bolzano-Vistas theorem. It is one of the cornerstone of the real analysis. Okay, without this, the real analysis theorem or any theorem of the Bolzano of the real analysis part cannot be proved. Okay, so and compact set and Hein-Borel theorem, these two will be discussed after Bolzano-Vistas theorem. Okay, so this is our what is called. We are going to finish. Mostly, we are going to finish this by next 2 or 3 lectures. Okay. Now, today, just I just want to end here. I think you have sent all your attendance. Mostly, you have sent. Okay. Only so much. Okay. Now you can leave now. Thank you very much. You will get it, and you will get the link uh, in the YouTube channel also, or in your college also. Okay, you can leave now. Thank you. I'm just stopping it.